All right, so let's go through our example and we'll write down all the things. We'll do the bootstrapping and we'll see what happens. Okay, we'll see if we actually do reject the null hypothesis. All right, so we're going to start with our hypotheses. So our null hypothesis is that the coin flip game is a fair game and the population proportion of heads should be 0.5. And the alternative is that it's a rigged game. We think the proportion is actually bigger than 0.5. Right, so part two, you take your sample. So we had a sample size of 100. We got 80 successes out of 100. We got 80 heads out of 100. So our sample proportion is 80 out of 100, which is 0.8. So that's not equal to 0.5, but so would, 53 out of 100 would not be equal to 0.5 either. We would not be suspicious about cheating if we won, if we only lost 53 times out of 100 instead of 80. So 80, is it different enough for us to say, okay, that's enough. We don't believe that this is a fair game. So we're going to open up StatCrunch. I'm going to use applets, resampling, and then I'm going to bootstrap a statistic. So I'm going to use proportion because this is a proportion confidence interval. And I've got 80 successes out of 100 observations. Click compute, and then I'm going to run this simulation 1,000 times, or no, 1,000 times, 10 times, so 10,000 times. And I'm going to look at, let's look at the 95% confidence interval. So that would be the 2.5th percentile and the 97.5th percentile. So my confidence interval is 0.72 to 0.87. So 0.72 to 0.87. So my confidence interval is 0.72 to 0.87 with 95% confidence. So we would call p hat the test statistic, and this is our bootstrapped confidence interval for the population proportion. So if we got 80 heads out of 100, we are 95% sure that the population proportion of heads is somewhere between 0.72 and 0.87. What was part three? Oh, that was part three. So this is part three. So now the part four is the decision. So since 0.5 is not in this interval, we're going to reject the null hypothesis because, we're 95% sure that the population proportion is between 0.72 and 0.87. And this assumption that the population proportion is 0.5 is outside of that. So we're going to say that this assumption is probably incorrect. So we're going to reject that statement. And now, since our confidence interval is completely above 0.5, we are going to support the alternative hypothesis that we believe the probability of getting heads is actually bigger than 0.5. So we're going to say there is sufficient evidence to support we'll say the claim, the hypothesis that P is greater than 0.5. Right, so that is the basic hypothesis test using a confidence interval, and we used a bootstrap sample to create that confidence interval. Now, let's talk about, since we're taking a 95% confidence interval, there's a 5% chance that, we're incorrect. And we actually rejected the null hypothesis was actually true. If that probability of getting 80 or more heads out of 100, even though it was really, really, really small, it wasn't zero, right? So if you decided to, say, take a baseball bat and break my legs because I cheated you in the game, and I actually didn't cheat, right? You would probably feel pretty bad about that, right? You're not going to take the baseball bat out if I only won 53 times out of 100, but you're going to be more tempted if I won 80 times out of 100. So we want to make sure that we are using the correct tolerance level. Okay, so let's go through what can happen in a hypothesis test. So, either the null hypothesis is true or it's false. So you assume it's true at the beginning, but it could be true, it could be false. You're going to reject the null hypothesis, or you're not going to reject it. So if the null hypothesis is true, we shouldn't reject it, right? So if we fail to reject and it was true, then that is what's supposed to happen. So that's a correct hypothesis test result. If the null hypothesis is false, then we should reject it. So in this case, that gets a check mark too. That is a correct result from a hypothesis test. Now, if the null hypothesis is true and we reject it, then that is a mistake, right? That is an error. So we call this a type 1 error, when you reject the null hypothesis when it's actually true. If the null hypothesis is false, then we should reject it. So if we don't reject the null hypothesis, then we make what's called a type 2 error. So a type 1 error is an assumption is made and you say that that assumption is false when it was actually true. And a type 2 error is a statement is made that is false and you say, I don't have enough evidence to say that it's false. I just don't have enough. So we actually consider the type 1 error to be worse, and we try to control that one. But the type 1 and type 2 errors are actually linked. And, if you make it too hard to make a type 1 error, you'll make more type 2 errors and vice versa. The best analogy for this is a jury trial. So if someone's on trial for murder, you're supposed to assume that they're innocent. So that's your null hypothesis, is that they're innocent. And if that assumption is false, then they're guilty. And then if you reject the null hypothesis, then you're convicting them. And if you fail to reject, then you acquit. So if you make a type 1 error, then you are sending a man to prison when they were actually innocent. And if you make a top 2 error, you're setting a man free when they were actually guilty. So a top 1 error is sending a guilty man, or sorry, sending an innocent man to jail, and a top 2 error is letting a guilty man go free. So our justice system is supposed to be set up to where it's, the top 1 error is worse and harder to do. I'm not saying that's actually what happens, though. Probably not. Okay. Now, you have to have a unanimous vote in the jury, right? So that makes it, harder to convict someone, right? But if you make it too hard to convict them, let's say you have to get unanimous vote from 1,000-person jury, then it would be too hard to convict someone if you have to convince 1,000 people, right? So you would end up making more top 2 errors. You would end up setting guilty men free more often if you've got to have 1,000-person jury have a unanimous decision. Okay. And then if you only leave it up to one person, then that one person is going to send more people, more innocent people to prison, because only one person has to agree, right? Has to make the decision. So you'll make more top 1 errors if you make it too easy to convict. All right. So we have to kind of balance it out. So we want to control the top 1 error by using what's called the significance level. So the significance level is, we use this Greek letter alpha for the significance level, and it is the probability of making a top 1 error. So really, we would like to have the significance level set first, and then we decide what kind of confidence interval we want to make. We usually pick values between 0.1 and 0.01. So these are usually between 0.01 and 0.1. So you can't set it to 0, because you would never convict guilty people. You would make more top 2 errors, and you can't make it too big. You can't make it like 0.3, because then you would send more innocent people to prison, right? So you would make more top 1 errors. So you want the top 1 errors to be small, but you don't want it to be 0. And the smaller you make it, the more top 2 errors you're going to make, but you'll make less top 1 errors. So if the consequences are high for making a top 1 error, you make your significance level low. Okay. So let's talk about how do we pick the confidence level based on our significance level. All right. So for our alternative hypotheses, we have 3 options. We have the less than, we have the greater than, and we have the not equal to. And it's going to be different based on these 3. So let's say that we have this should be not equal to. Let's say we have a not equal to hypothesis, alternative hypothesis, and we're going to use a confidence interval. Then we want to set our confidence level to 1 minus the significance level. So let's just draw a normal distribution here. That's usually what we get. So we want the confidence level to be equal to 1 minus the significance level. So these tails on the side, when you put those two together, you get alpha. Okay, that means in each one you got alpha over 2. But those put together would be the probability of making the top one error. So just by random chance, if you fall into one of these tails, then you're outside of the confidence interval, right? So the confidence interval is defined by this confidence level in between, right? We would find the markers that divide that middle area. So if it's 95%, then this is the middle 95%. So, this would be your lower limit of your confidence interval. This would be your upper limit. So the probability of falling outside of that would be alpha. And if you fall outside of that, then you're going to reject the null hypothesis. So this would be the probability of just by random chance you fall into these tails, right? Right, let's take a look at less than. So if you have a confidence interval and you want that entire interval to be below the assumption in order to make that, in order to reject that null hypothesis, right? Your P naught is actually going to be completely above your confidence interval. Okay, so we're just going to look at this tail, and that's got to be alpha. So this tail is also alpha. So our confidence level, it's got to be 1 minus 2 alpha. Okay, and that'll give us the right confidence interval. And if that entire confidence interval is below our assumption for the null hypothesis, then we will reject the null hypothesis and we'll support the alternative hypothesis. Right? And then same thing for greater than. So if we want our entire confidence interval to be above our assumption for the null hypothesis, then it's, that assumption has got to be in this left tail. So that's got to be alpha. And same thing on the other side. And again, our confidence level will be 1 minus 2 alpha. So we'll really set our significance level first, and then we'll make the confidence interval that goes with that based on our alternative hypothesis. And then we'll make the confidence interval, and then we'll see where that confidence interval is relative to the assumption made by the null hypothesis.